Facet counts are easy to get wrong, and users notice immediately. This is the pattern you'll be able to implement by the end, which filters a query and returns items with correct facet counts. I'm Professor Pi, teaching search and IR with simple Python. Imagine an e-commerce search where shoppers filter by color and brand. They click red, expect to see red items. But they also expect the brand counts to show how many items each brand has if they keep the color filter. If counts collapse to only the remaining hits, the UI becomes confusing. That confusion kills trust and exploration. Elasticsearch can do faceting and aggregation very quickly, but the default placement of filters can make counts reflect only the visible hits. We want counts that help users pivot, not hide options. The intuitive idea is simple. We want two things at once. First, return only the hits that match the user filters. Second, compute facet counts over a slightly different set, typically the full set constrained by some filters, but excluding the facet itself. That way, the user sees correct alternatives. It makes faceted navigation feel honest and useful. Strengths are clarity and predictable UX. One downside is a little extra query planning, but Elasticsearch was built for this. We will build a tiny example with a few product documents. I will show the basic connectivity, then how naive filtering affects counts, and then the post-filter pattern that fixes counts. Finally, we will show how to compute per facet counts that exclude the facet's own selection so the counts remain meaningful. Keep calm. The code is short, and the ideas map directly to production. Now we'll confirm our Elasticsearch connection. This snippet creates an Elasticsearch client using the official Python driver and points it at a local node. The variable s is the handle used for all subsequent search and aggregation calls. The variable OK stores the result of es.ping, which makes a lightweight HTTP request to confirm the cluster is reachable. A simple print shows whether the server responded as expected. If you run multiple nodes or protect the endpoint, this is where you would confirm connectivity before any data work. The printed result confirms the client can talk to Elasticsearch, which is essential before building facets. Next, we'll index a few small documents and run a base aggregation. This example writes 3 simple product documents using the Elasticsearch client's es.index call. The list docs hold small fields we will facet on, including brand and color. After writing, es.indices.refresh makes the document searchable immediately. The es.search call sets size equals 0 to skip hits and requests a terms aggregation named brand on brand keyword, which counts documents by brand. The variable b collects the aggregation buckets and pair sorts them for stable output. Increasing the size parameter fetches more unique brands at higher memory cost. Decreasing it can miss rare brands. The printed result shows base facet counts with no filters applied. Now we'll show the common pitfall where a filter hides facet counts. This snippet builds a bool filter query in the variable q that requires color equal to red. The es.search request uses query q and again asks for a terms aggregation on brand.keyword. Because the filter is inside the query, both hits and aggregation counts are restricted to red documents. The list B contains buckets only for brands present in the filtered subset, and pairs sorts the output. This behavior is often perceived as wrong for faceting when users expect counts that help them pivot to other brands. The printed result shows counts limited by the color filter, illustrating the pitfall. Next, we'll separate hit filtering from aggregation scope. This snippet moves the color filter to the post filter parameter in the elasticsearch-py call. The query is match all, so aggregations run over the full result set, while post filter limits only the returned hits. The variable B now reflects facet counts from all documents, regardless of the color filter, which keeps options visible for users to pivot. The sorting step keeps the printed order stable. Increasing term size can improve completeness at some memory cost. Reducing it risks truncating rare buckets. The printed result shows brand counts are global again, even though hits would be read only, which is a key faceting pattern. Now we'll compute per facet counts that exclude the facet selection itself. This example applies two hit filters via post filter. Color equals red and brand equals Acme, so hits are narrowed. The aggregation X is a filter aggregation that applies only the color constraint, intentionally omitting the brand filter. Inside X, the terms aggregation T computes brand counts within the red scope. The variable B collects these buckets, which now show what alternatives exist if users toggle brands while keeping color fixed. This pattern delivers correct per facet counts under current filters while excluding the facet's own selection. The printed result proves Xeon remains a viable option under red, enabling a product-style faceting UX. In a real project, this pattern maps to each facet you display. For every facet column, run an aggregation that mirrors user filters but excludes the facet's own value. That way, the UI shows both filtered hits and useful counts for exploration. Recap 1. This is about separating aggregation scope from hit filtering so counts are actionable. 2. Use post filter to keep aggregations broad while limiting returned hits. 3. Caveat: more per facet work can raise query complexity and memory use, so tune the term size and aggregation structure. Next step: extend this pipeline by computing per facet exclusions for every visible facet and measure latency as you increase the number of facets and term size. If practical, hands-on IR helps. Subscribe and watch the IR videos.